Now in this session I'm going to explain about the analysis of RL circuit for different functions. So analysis of RL circuit for various functions. This concept I'm going to explain. After completion of this analysis of RC circuit for various functions, I will explain. So there is an RL circuit. It is an RL circuit which was excited by some source. So it is V of t, and it is the switch which was closed at t is equal to 0. It is R and it is L. So in this analysis of RL circuit for various functions using Laplace transforms, the current that is flowing through this is I of t. You can see here, draw the frequency domain network. It is a time domain network. We need to draw the frequency domain network to analyze this RL circuit using Laplace transforms. Here for various functions means if the excitations are different, if the excitation is step function, how will be the response of this RL circuit? If the excitation is ramp function, impulse function, how will be the response of this RL circuit using Laplace transform? I am going to explain here. So for that, first we need to understand here is at t is equal to 0 minus, the switch is open. At t is equal to 0 only, the switch was closed here. T is equal to 0 minus, the switch is open. So the current that is flowing through this inductor is 0, and that is equal to I of 0 plus, because inductor doesn't allow the sudden changes in current. So I of 0 is equal to 0 amperes. So this is the initial current that I require to draw the frequency domain network of this time domain network, or the transformer network. The frequency domain network can also be called as transformer network, which transforms from time domain to S domain or frequency domain. Now draw the transformer network here. I am going to draw the transformer network. So this is V of S. It is V of S, and the switch was here for t greater than 0. It is R, and here it is Ls. Here this is minus and plus. It is L into I of 0. The value of I of 0 is 0 anyway, so it will act as short circuit, and it is R here. So this is I of S. Now this I of S is equal to this voltage source V of S divided by this resistance plus Ls, R plus Ls. Since the magnitude of this voltage source here is 0, it will act as short circuit. So I of S is equal to now V of S divided by, if I take L as common here, L into S plus R by L. Now for various functions of the excitations, how will be the response of this RL circuit using Laplace transform? I am going to analyze here. So first one, for step function. For step function, what is step function? It is normally indicated as U of t. So if V of t is equal to U of t, then what is the response I of t? I need to calculate here. So V of S is equal to, if I apply the Laplace transform, u of s is equal to a divided by s. You know this information. Now if you calculate this I of s, that is equal to v of s is a by s, a divided by l into s plus r by l. Now I of s is equal to, so it is a by l divided by s into s plus r by l. So to find this I of t, I need to apply the inverse Laplace transform for this equation. So to apply the inverse Laplace transform, I need to do the partial fractions for it. So I of s is equal to this a by l divided by s into s plus r by l is equal to some constant. So let us assume it is k1 divided by s plus k2 divided by s plus r by l. So I need to find the value of k1 here. To find the value of k1 is equal to, it is this function s into I of s at s is equal to 0. So s into I of s is a by l divided by s into s plus r by l at s is equal to 0. So now this s and this s will get cancelled here. So substituting s is equal to 0, a by l divided by r by l, so it is a by r. So the value of k1 here is a by r. Next, to find this k2 is equal to, what is this? It is s plus r by l, s plus r by l into I of s at s is equal to minus r by l. So now s plus r by l into I of s is a by l divided by s into s plus r by l at s is equal to minus r by l. Now this at s plus r by l will get cancelled. So a by l minus r by l, so it is minus a by r. So the value of k2 is minus a by r here. So I found the values of this a by r, k1 and k2. Let us substitute this k1 and k2 in this equation. Then I get I of s is equal to, it is k1 divided by s plus k2 divided by, k1 value is a by r divided by s minus a by r divided by s plus r by l. So these are the values of k1 and k2. After substituting these values, let us apply the inverse Laplace transform for this equation. So inverse Laplace transform of I of s is equal to I of t, that is equal to, if I take a by r as a common, it is for 1 by s, the inverse Laplace transform is, I can write it is 1 minus the inverse Laplace transform for 1 by s plus r by l is e power minus r by l into t. So the expression for it is I of t is equal to a divided by r into 1 minus e power minus r by l into t. So this is the response for the step function. For unit step function, the value of a here is the magnitude of the unit step function, a is equal to 1. So for unit step function, the response is I of t is equal to 1 by r into 1 minus e power minus r by l into t. So this is the response of RL circuit if you apply the unit step function as an excitation for the RL circuit. Now second one, if you apply the ramp function, that is R of s. Now for the ramp function, you know that R of s is equal to a divided by s square, and the excitation is V of s is equal to R of s for ramp function. So that is equal to a by s square, and we know that I of s is equal to V of s divided by l into s plus r by l. So I of s is equal to V of s divided by L into s plus R by L. And let us substitute this V of s, that is A divided by L into s square into s plus R by L. So this is I of s. And now to find the inverse Laplace transform for this expression, I need to do the partial fractions for it. So these partial fractions, here the partial fractions for 1 by s square into s plus R by L. I am going to find the partial fractions only for this function. That is equal to some k1 divided by s plus k2 divided by s square plus k3 divided by s plus R by L. Now let us cross multiply taking the LCM of s square into s plus R by L. So it is k1s into s plus R by L plus k2 into s plus R by L plus k3 into s square. That is equal to 1 divided by s square into s plus R by L. Now this thing and this one will get cancelled here. So 1 is equal to, so write down this s square coefficients, s square into k1 here plus k3. So this term and this term is over. Next s coefficients plus s into k1 into R by L plus k2. So this term and this term is over. Next constant k2 into R by L, k2 into R by L. So comparing s square s and constant terms on both sides of this equation, k1 plus k3 is equal to 0, k1 into R by L plus k2 is equal to 0, k2 into R by L is equal to 1. So from this k2 is equal to L by R. So this is the value of k2. Now substitute this value in this equation. K1 into R by L is equal to minus k2, that is equal to minus L by R. So it is k1 into R by L. So k1 is equal to, it is minus L by R whole square. So this is the value of k1. Next k3 is equal to, k1 plus k3 is equal to 0. So k3 is equal to minus k1. So k3 is equal to L by R whole square. So these are the values of k1, k2 and k3. Now substitute these k1, k2, k3 values in this expression. So I can write I of s is equal to, take a by L as a common, a by L. So this term 1 by s square into s plus R by L is this one. So into, it is k1 is minus L by R whole square divided by s plus k2 is L by R divided by s square, k3 plus L by R whole square divided by s plus R by L. Now this L, if I take a L in all these things, so I will get A into, it is minus L divided by R square into 1 by s plus 1 by R into 1 by s square plus L by R square into 1 by s plus R by L. Now if you apply the inverse Laplace transform for it, if you apply the inverse Laplace transform for this I of s, that is L inverse of I of s is equal to I of t, that is equal to A into is minus L by R square. For 1 by s, the inverse Laplace transform is 1. plus 1 by r into, for 1 by s square the inverse Laplace transform is t plus L by r square into, for this 1 by s plus r by L the inverse Laplace transform is e power minus r by L into t. So this is the expression for I of t. So I of t I can write for this, it is for unit step function, for unit ramp function, a value is 1. So this expression is will become minus L by r square plus 1 by r into t plus L by r square into e power minus r by L into t. So this is the expression for unit ramp function. Here I can take it out this L by r square as a common. I of t is equal to, if I take this, so first write 1 by r into t plus L by r square, minus L by r square. You take this minus L by r square as a common, it is e power minus r by L into t, it is minus 1, plus 1 it is. So if I take this, it is minus L by r square, this is it is minus, and it is plus 1 for t greater than 0. So this is the expression if you apply unit ramp function for the RL circuit. Next thing, if you apply impulse function, third one is for impulse function. For impulse function, that is delta of t or delta of s. If you apply the Laplace transform for delta of t, that is equal to 1. So v of t is equal to delta of t here. So v of s is equal to Laplace transform of delta of t, that is equal to 1. So I know that I of s, the expression for I of s is equal to v of s divided by L into s plus r by L. So just now we got this expression. So I of s is equal to v of s divided by L into s plus r by L. So instead of v of s, if you replace with 1, I of s is equal to 1 divided by L into s plus r by L. So for unit impulse function it is 1. So it is for unit impulse function. Unit impulse function, it is this one. So I of s is equal to this one. So if I apply the inverse Laplace transform for it, then it is equal to I of t, it is equal to 1 by L into e power minus r by L into t for t greater than 0. So this is the expression for impulse function. Now solve one problem here on this functions, different functions. So here this is the problem, is this one, plus and minus is an RL circuit. It is an RL circuit. The L value is 1 Henry, R value is 1 ohm, and the switch was closed at t is equal to 0, and this is the current I of t, and this is the voltage V of t, and this voltage waveform he has given that. So this is the voltage waveform. So it is 1 and it is 1 here. The magnet is 1 and pulse width also is 1. So it is V of t. This is the time t is 0. What I need to find here is, I need to find this I of t. So I need to obtain I of t for t greater than 0 if you apply this function. So how to solve this? See, so first let me define this okay. So at t is equal to 0 minus, the switch was open. At t is equal to 0, the switch was closed just at t is equal to 0 plus, just after switching action is done. So at t is equal to 0 minus, the current flowing through the inductor is I of 0 minus is 0 amperes, that is equal to I of 0 plus, and I of 0 is 0 amperes. So now for t greater than 0, so draw the transformer network or frequency domain network. This plus and minus, it is V of S instead of V of t. I need to write V of S here. The switch was closed t greater than 0, for t greater than 0. So resistance is 1 ohm, and this is Ls. This value is L into S. So that is S. L value is 1, and here there is a magnet of voltage here. This voltage value is L into I naught. So I of 0. So I of 0 value is 0. So this magnet of voltage is 0. 0 means it is short circuiting. So this is the function, it is I of S. Now, so this I of S is equal to V of S divided by, it is S plus 1. V of S divided by S plus 1. The impedance of this circuit is S plus 1. Now, to find this I of S, I need to write this V of S here from this diagram. So this signal I can write as, see, this is U of t is this one. So for t greater than 0, this time this is step function U of t. So U of t is 1 for t greater than 0. Now this one, it is 1, pulse width is 1, and the magnet is 1 here. It is U of t minus 1. U of t minus 1 signal is like this. So if I subtract this signal from this signal, that is U of t minus U of t minus 1. That means from this total, if I subtract this one, only I will get this signal. So this is 1 and this is 1. Okay, so this signal I can write as U of t minus U of t minus 1. So finally what I want to say here is, whatever the signal that he has given as an excitation, V of t is equal to U of t minus U of t minus 1. So V of S is equal to 1 by S minus, it is e power minus as, a value here is 1. So e power S divided minus S divided by S. So it is 1 minus e power minus S divided by S. So this is V of S. So if I substitute this equation in this expression, I of S is equal to V of S value. V of S value is 1 minus e power minus S divided by S into S plus 1. So it is 1 divided by S into S plus 1 minus e power minus S into 1 divided by S into S plus 1. So this 1 by S into S plus 1, for 1 by S into S plus 1, this is it is I of S. I can write as S plus 1 minus S divided by S into S plus 1. So this is 1 by S into S plus 1, I can write as S plus 1 minus S divided by S into S plus 1. This S and this S will get cancelled, so 1 divided by S into S plus 1. So I can write it as S plus 1 will get cancelled, 1 by S minus 1 by S plus 1. So this one I can write as 1 by S minus 1 by S plus 1. So for this, if I apply the Laplace transform, inverse Laplace transform for it, it is U of t minus, for U of t it is 1 by S. For this one it is e power minus t into U of t. I can write as U of t minus e power minus t into U of t. Now this is the inverse Laplace transform for 1 by S into S plus 1. For e power minus S, as per frequency shifting theorem, the Laplace transform for 1 by S into S plus 1, 1 by S into S plus 1, the Laplace transform is U of t minus e power minus t into u of t. Then Laplace transform of e power minus s into 1 by s into s plus 1 is equal to, so it is u of t minus 1. In place of t, I need to replace with u of t minus 1. It is e power minus t minus 1 u of t minus 1. So for this I of s is equal to 1 by s into s plus 1 minus e power minus s divided by s into s plus 1. If I apply the inverse Laplace transform for it, L inverse of I of s is equal to I of t is equal to, so the inverse Laplace transform for it is u of t minus e power minus t into u of t, minus the inverse Laplace transform for it is u of t minus 1 minus e power minus t minus 1 into u of t minus 1. So take this one as a common. I of t is equal to u of t as a common here, u of t into 1 minus e power minus t, here minus u of t minus 1 as a common, it is 1 plus e power minus t minus 1. So it is plus here, I think it is plus. Why? Because here it is bracket, I forgot to place the bracket here. So minus into minus, it is plus. If I take the minus, so it is 1 minus, sorry, u of t minus 1 is a common, e power minus t minus 1 into u of t minus 1. So this is the expression or response for this problem if this type of signal is applied as an excitation for this RL circuit. Next problem, here this is the circuit. The circuit here is, this is the source and this is R L circuit. At t is equal to 0, the switch is closed here, it is I of t, and this is 2 into delta of t minus 3. This is the excitation input. This value is 2 ohms and this value is 1 Henry. So for this type of problem, solution, we know that I of 0 minus at t is equal to 0 minus I of 0 minus is 0, that is equal to I of 0 plus, so I of 0 is equal to 0 amperes. Now for t greater than 0, this circuit I can write it as transformed circuit. The switch was closed here, it is 2 ohms and it is LS, L value is 1, so it is S. So there is no voltage source here since I of 0 is 0, so it is this one, and this value is 2 into this e power minus 3s into 1. So the Laplace transform for 2 into delta of t minus 3 is actually for delta of t, the Laplace transform is 1. Since here it is t minus 3, so it is 2 into here 2 into e power minus 3. This is the Laplace transform for this one. Now let us apply this I of s here. So I of s is equal to 2 into e power minus 3s divided by s plus 2. So the Laplace transform, inverse Laplace transform for 1 by s plus 2 is this e power minus 2s. So the inverse Laplace transform for e power minus 3s divided by s plus 2 is, so e power minus 2t, this e power minus 2t is equal to, it is e power minus 2 into, in place of t I need to replace with t minus 3. So from this, if I apply the inverse Laplace transform for I of s, that is equal to I of t, so it is 2 into e power minus 2 into t minus 3. So this is the a response for this RL circuit if we give the excitation as this function. Here we need to write this u of t minus 3 also here. Actually it is u of t. Since it is 2 minus 3, sorry, it is for this one it is u of t. 1 by s plus e, I can write as e power minus 2t u of t. U of t value is 1. So it is u power minus 2t. But it is not 1 by s plus t 2. It is e power minus 3s by s plus 2. So it is u of t minus 3. It is for t greater than 0. For t greater than 0. Another problem on this RL circuit itself. Different problems. Here this is the sinusoidal input. Now we are giving as sinusoidal input. It is an RL circuit. So this value is 5 Henry. This value is 10 ohms and the switch was closed at t is equal to 0. This is the current I of t and the input for this is 50 sin 25t. So this is the excitation input for this RL circuit. Now solution at t is equal to 0 minus I of 0 minus is 0, that is equal to I of 0 plus, so I of 0 is 0 amperes. For t greater than 0, so transformer network, draw the transformer network. So if you apply the Laplace transform for it, 50 into, so sin 25 omega t, so the Laplace transform for sin 25 t is sin omega t. The Laplace transform is omega divided by s square plus omega square. S square plus 625. Omega square 25 whole square is 625. So it is 50 into. So it is 50 into this one. So 50 into 25 divided by s square plus 625. And the switch was closed here. This is 10 ohms and this is Ls. So it is 5 into S. There is no magnitude of voltage here because L into I of 0 is 0, since I of 0 is 0. So it is I of S. Now write down this I of S expression here. I of S is equal to, it is if you multiply this 50 with 25, you will get 1250. It is 1250. So it is 1250 divided by s square plus 625. So it is 1250 divided by s square plus 625. It is V of s divided by this 10 plus 5s. 10 plus 5s. So this is the expression for this circuit, for this I of s. So now I of s is equal to 1250 divided by, if I take 5 as common here, 5 to s plus 2 into s square plus 625. So this 525s 250 times, 25 5s are 125, so 250. So it is 250 divided by, it is s square plus 625 into s plus 2. So it is I of s. So I need to do the partial fractions for finding this inverse Laplace transform for this I of s. So let us take it is as plus b divided by s square plus 625 plus c divided by s plus 2. So this is equal to 250 divided by s square plus 625 into s plus 2. So now after here it is cross multiply all these things here. Here as plus b into s plus 2 plus c into s square plus 625 divided by s square plus 625 into s plus 2. It is 250 divided by s square plus 625 into s plus 2. This one and this one will get cancelled here. So write down the s square terms here. S square coefficient is a plus c plus s coefficients. So it is 2a plus b, 2a plus b is 2a plus b, and here there is no s coefficient here, plus constant term 2b plus 625c, that is equal to 250. So if you compare, after comparing s square comma s and constant terms, coefficients on both sides of the equation, values of a here is, a value we get as minus 0.397 and b value is 0.795 and c value here is 0.397. So these are the values that we will get after comparing and solving the equations. 3 equations we will get. After solving these equations, we will get these a, b, c values are like this. Now let us write this I of s here. I of s is equal to 250 divided by s square plus 625 into s plus 2 is equal to, this a value, a is plus b, a value is minus 0.397 into s plus b value is 0.795 divided by s square plus 625 plus c value here, c value is 0.397 divided by s plus 2. So I need to find this I of t here. So let us take the inverse Laplace transform. L inverse of I of s is equal to I of t is equal to it is minus 0.397 into L inverse of s divided by s square plus 625. So it is 25 whole square it is. So s divided by s square plus omega square, this value is cos 25t. So it is cos 25t. This is the inverse Laplace transform. Plus this one I can write as 0.795 divided by 25 into, it is 25 divided by s square plus 25 whole square. So the inverse Laplace transform for it is sin 25t plus it is 0.397 to e power minus 2t. So this value 0.795 divided by 625, I can write this one as 0.032. So this value is minus 0.397 cos 25t plus 0.032. If you calculate this value, you will get this one, sin of 25t plus 0.397 e power minus 2t. So this is the expression for I of t for t greater than 0. Now let me explain the response of RC circuit. Response of RC circuit or analysis of RC circuit using for various functions or for various excitations or various functions using Laplace transforms. So let us consider an RC circuit here. So this is an RC circuit switch whose electrical supply is controlled by some switch here. So it is RC. This is some function, it is V of t, and the switch was closed at t is equal to 0. so that the current will circulate through this, that is I of t. So for various functions of excitations, for step function, for ramp function, for impulse function, how will be the response of this RC circuit using Laplace transform technique, we are going to analyze here. Now at t is equal to 0 minus, the value of the voltage, the switch was opened here, the switch is closed at t is equal to 0 only, at t is equal to 0 minus, the switch was open, so the value of the voltage across this capacitance is V of 0 minus is equal to, that is Vc of 0 minus is equal to 0 volts, so no supply is connected, so it is 0 volts, that is equal to Vc of 0 plus, so Vc of 0 is equal to 0 volts only. So while we are drawing the transformer network or frequency domain network, so here for t greater than 0, I am drawing the transformer network by taking the Laplace transform, it is V of s. So the switch was closed here for t greater than 0, so this is the resistance R, and this was the capacitance, it is 1 by Cs, and I need to place the voltage source here, that whose value is Vc of 0 by s. So Vc of 0 is 0 volts here, so 0 by s is 0, so it will act as short circuit, so directly I am writing here, so it is a circuit, so it is I of s. Now if I write this I of s expression here, I of s is equal to V of s divided by R plus 1 by Cs. Now I of s is equal to V of s divided by RCS plus 1 divided by Cs. So that is equal to V of s into Cs divided by, if I take RC as a common here, S plus 1 by RC. So this C and this C will get cancelled here, so it is I of s. So I of s is equal to V of s divided, V of s into S divided by R into S plus 1 by RC. So this is the I of s equation. Let us assume it as equation 1. Now case 1, for step input, that is V of s is equal to some A divided by S, that is U of t. U of t is A divided by S. A value is some constant. For unit step function, A value is 1. For step function with magnitude of 10, then A value is 10. So this is V of s. Now I of s is equal to some A divided by S into S divided by R into S plus 1 by RC. So this S will get cancelled here. So I of s is equal to A divided by R into S plus 1 by RC. And if I the response for this time response, if you want to calculate the time response, take the inverse Laplace transform for it. I of s is equal to I of t is equal to A divided by R into e power minus 1 by RC into t. So this is the response for step response for this RC circuit. For unit step function, the value of A here is 1. So I of t is equal to 1 divided by R into e power minus 1 by RC into t. So this is the response. That is for unit step per response. Next here is for ramp signal. Case 2 here is case 2. For ramp input, this R of t. So you know that R of t is equal to A into t, and V of t is equal to R of t. The input is V of t is equal to R of t. V of s is equal to R of s is equal to A divided by s square. Now what is the value of I of s? From equation 1, I of s is equal to V of s into s divided by V of s into s divided by r into s plus 1 by rc. So this is the value of I of s from equation 1. Now let us substitute this value of r of v of s here. So it is a divided by s square into s divided by r into s plus 1 by rc. This s and 1s will get cancelled, so it is a divided by r into s plus 1 by rc. So this is I of s. So now it is a divided by r, just I am multiplying with 1 by rc, sorry, rc into 1 by rc divided by s into s plus 1 by rc. So this rc will get cancelled, so same equation will get here. So a divided by r into rc into this 1 by rc I am writing like this, s plus 1 by rc minus s divided by s into s plus 1 by rc. So this s and this s will get cancelled, so 1 by rc same will be remain here. So it is r into c, sorry, it is a into c into, it is s plus 1 by rc, 1 by rc. So 1 by s minus 1 by s plus 1 by rc. So it is I of s. So now I of t is equal to, so a into c into, for this the expression for 1 by s is, if you apply the expression, it is 1 minus, sorry, the inverse Laplace transform for 1 by s is 1, and the inverse Laplace transform for 1 by s plus a is e power minus at, that is e power minus 1 by rc into t. So this is the expression for t greater than 0. For unit ramp function, a is equal to 1. So I of t is equal to c into 1 minus e power minus 1 by rc into t. So it is for t greater than 0. This is the expression for I of t. This one. Next, case number 3. For impulse function, that is delta of t. Normally delta of t is equal to some with a magnitude of a, and delta of Laplace transform of delta of t is equal to a here. For unit impulse function, Laplace transform of delta of t is equal to 1. So I of s is equal to, know that I of s is equal to v of s into s divided by r into s plus 1 by rc. So this is the expression from equation number 1. Now this v of t here is, v of t is equal to delta of t, and v of s is equal to delta of s is equal to, for unit impulse function it is 1. So it is so if I substitute I of s is equal to, v of s is equal to delta of s is equal to 1 into s divided by r into s plus 1 by rc. So I of s is equal to s divided by s plus 1 by rc to r. It is this one. I can write this one as 1 by r into this s plus 1 by rc minus 1 by rc divided by s plus 1 by rc. So this 1 by rc will get cancelled, so s divided by s plus 1 by rc will remain here. So 1 by r into, it is 1 minus 1 by rc, it is into 1 divided by s plus 1 by rc. Now if you apply the inverse Laplace transform for this I of s, inverse Laplace transform of I of s is equal to I of t is equal to, so for it is 1 by r as a constant, it is 1. The inverse Laplace transform for 1 is delta of t minus 1 by rc into, it is e power minus 1 by rc into t. So this is the I of t expression for t greater than 0. So this is the response of RC circuit for different types of functions. Now let us solve some of the problems regarding to this RC function with different excitations. Here there is a problem on this RC circuits. So this is plus and minus, this is R value, C value 1 farad, and the value of this excitation here is 2 into R of t minus 2, and the switch was closed at t is equal to 0. This is I of t, and the value of the resistance here is 3 ohms. So what I need to find here is, I need to find I of t for t greater than 0 if the switch is closed at t is equal to 0, and the excitation input is delayed or shifted ramp function. So here the same thing, at t is equal to 0 minus, Vc of 0 minus is equal to 0 volts, that is equal to Vc of 0 plus. So Vc of 0 is equal to 0 volts. Now for t greater than 0, draw the transformed network. So Laplace transform of 2 into R of t minus 2. For this the Laplace transform is, we know that for R of t the Laplace transform is a by s square. Here the a value is 2 here, so the magnitude is 2 here, so 2 into, so this it is unit ramp function, so it is 1 by s square for this R of t 1 by s square. Since it is not R of t minus 2, so it is e power minus 2s divided by s square. So this is the Laplace transform for this excitation. Now this input is given at t is equal to 0, close the switch, and this value is 3 ohms, and the capacitance value is 1 by cs, that is 1 by c value is 1 here, so 1 by s, and this value of this excitation here is plus and minus, it is 2 into e power minus 2s divided by s square, and this value is I of s. Now I of s from this is equal to 2 into e power minus 2s divided by s square divided by 3 plus 1 by s, that is equal to 2 into e power minus 2s divided by s square divided by 3s plus 1 divided by s. So this 1s will get cancelled here, so it is equal to 2 into e power minus 2s divided by this s into 3s plus 1. If I take 3 as a common here, so it is 2 by 3 into e power minus 2s divided by s into s plus 1 by 3 value is 0.333. So this is the I of s. So now I am going to do the partial fractions for this function, s into s plus 0.333. So this, to find this, it is 1 by 3 is also there, so 1 by 3 into, that is 1 by 3 into, for this I am going to find the partial fractions. 1 by 3 value is 0.333 divided by s into s plus 0.333, that is equal to s plus 0.333 minus s divided by s into s plus 0.333. I can write like this. So this 1 by 3 value is 0.333. So this s and this s will get cancelled. So finally what we got here is this one. So this one I can write as 1 by s minus 1 divided by s plus 0.333. So it is the expression for this function s plus 0.333. So now I of s is equal to, so 2 into e power minus 2s, 2 into e power minus 2s. So this 1 by 3 into s into s plus 3, I can write as 1 by s minus 1 by s plus 0.333. It is I of s is equal to now 2 into e power minus 2s into 1 by s minus 2 into e power minus 2s into 1 by s plus 0.333. Now the inverse Laplace transform for this one I of s is equal to I of t, that is equal to, for 1 by s the inverse Laplace transform is u of t, but here it is e power minus 2s is that, so it is 2 into u of t minus 2. Here the 1 by s plus 0.33 is, the expression is e power minus 0.33. So since it is 2 here, 2 into e power minus 0.33 t, here it is e power minus 2s is there. So instead of t, here it is 2 minus 2 into u of t minus 2. It is for t greater than 0. So this is the expression. This is the expression for the response of this current, 2 into u of t minus 2 minus 2 into e power minus 0.33 into t minus 2 into u of t minus 2. Next, another problem here is this plus and minus delta of t, this which is it is 2 farads, it is 5 ohms, the switch is closed at t is equal to 0, and this is I of t. So I need to find the expression for I of t for t greater than 0 when the switch is closed at t is equal to 0. Same procedure I need to apply at t is equal to 0 minus, the value of V2 of 0 minus is equal to 0 volts. The voltage across this 2 farad is V2, it is V2 of 0 plus. So V2 of 0 is equal to 0 volts. Since no supply is connected for this RC circuit at t is equal to 0 minus, the voltage across this capacitance 2 farad is 0. So now for t greater than 0, let us redraw the circuit. The Laplace transform for delta of t, we know this, it is 1. So it is plus and 1 minus, it is 1, and the switch was closed here, it is 5 ohms, and it is 1 by Cs. So this Cs value here is 1 by 2s, and it is I of s. So I of s is equal to, it is 1 volt, 1 divided by 5 plus 1 by 2s. So it is, I can write as 2s divided by 10s plus 1. So if I take 10 as a common here, it is 0.2 s divided by s plus 0.1. 2 by 10 is equal to 0.2. So this is I of s. So this s divided by s plus 0.1, I can write as s plus 0.1 minus 0.1 divided by s plus 0.1. So the same thing I can write like this. So it is 1 divided by, so it is 1 minus 0.1 divided by s plus 0.1. S plus 0.1. So here for I of s, it is 0.2 into, it is 1 minus s divided by s plus 0.1 is 0.1 divided by s plus 0.1. So it is 0.2 minus 0.02 divided by s plus 0.1. So this is I of s. So the inverse Laplace transform for this I of s is I of t, that is equal to 0.2, it is 0.2 into delta of t minus 0.02 into e power minus 0.1 t. It is for t greater than 0. So this is the response for this circuit if you apply this impulse function as an input. Here I forgot one thing here. It is I need to write u of t here. Since this delta of t is coming to picture, I need to write this u of t also here. U of t values anyway it is 1.